Recording is on. Good
Okay,
luck.
everyone. Thank you. Welcome back to our second session regarding the first part of our AI series. Um, on Tuesday, we talked about basic introduction to deep learning. We discussed about the perceptron algorithm, the feed-forward architecture, which is the most basic architecture of neural networks. We talked about activation functions, the gradient, stochastic gradient descent, training algorithm, and about loss functions. Um, okay, I will start sharing my screen um, and do a bit I just want I just want to remind the most important stuff from Tuesday. Okay, I hope everyone sees my screen. I will start by reminding you the basic training steps for the algorithm using this diagram. Uh, you can see from left to right, we have the feed-forward step or the prediction step. We take the inputs, we take their weights, we compute the sum of products, and then we take them we apply the activation functions, we get the output or the prediction. We then apply the loss function in order to compute the loss or the error of the prediction by comparing the prediction with the actual label from the input dataset. And then using this loss, we go back and propagate the error in order to adjust the parameters, which means the weights and the biases for each neuron on each layer. In order to do so, we use what I explained, what I showed on Tuesday, called stochastic gradient descent, which uses the gradient of the loss function and of the activation functions in order to update the weights. Why use the gradient? Because the gradient gives the slope of the tangent of the graph of the function. Therefore, it shows the direction in which um, the function increases. So we need to go in the opposite direction in order to reach the global minima of the loss function, which means that we want to go to the global minima of the error. Um, we repeat this process for each element from the input data set. And after we used every element from this data set, we can say that we completed a training epoch. And usually training is done in a large number of epochs, usually hundreds, thousands, or even more depending on the data set and the use case. Okay, let's talk about some other concepts regarding the training. First, we have what we call the parameters, which are basically the core part of each network. The weights and the biases, these parameters are adjusted during training in order for we can say that by adjusting these weights, the model learns. This is what training means, adjusting the weights and the biases. Uh, Usually in practice, models have a very large number of weights and biases. For example, the latest model from GPT 4.0, or I think it's even a newer one, has billions of such parameters, which were trained on trillions of words, combination of words from different languages, and so on. We also have what we call hyperparameters. These basically define the training configuration. So the parameters are related to the model. The hyperparameters are related to the training procedure. So hyperparameters include the number of training epochs, the learning rate, which is the small rate by which we do the training, a small value, usually between 0 and 0.5. The mini batch size, which I mentioned, is a procedure in which we don't update the network after each element from the dataset, but we take chunks from the dataset and use the whole chunk in order to update. This is a bit more memory efficient, and also it's better to use this procedure because if we have a lot of noise or outliers, the update is then averaged on the whole chunk, so we don't have a lot of interference caused by noise. Hyperparameters also include the number of hidden layers and the layer size, basically define the shape of the model or the network. Hyperparameters also include the list of activation function. Usually we have the same activation function on one layer, and then we can use different activation functions based on each layer. Like I showed you on Tuesday, usually, for example, the output layer usually uses an activation function because we want to restrict the output in a given range. For example, we can use sigmoid or a logistic function in order to limit the output between 0 and 1. We can use softmax in order to obtain probability distribution, especially for multi-class classification. So this is how activation functions are defined as hyperparameters. And one last hyperparameter is the optimizer, which is basically the algorithm, the training algorithm that we use in order to update the parameters. So last time I showed you stochastic gradient descent, which is a great start for didactic applications and also for simpler tasks. This does the job well. But some of the shortcomings of this stochastic gradient descent is that it can be slow and it can get stuck on the local minima. So if you remember, let me show you this here. If you remember, I showed you this is the surface. If we were to plot the loss function three-dimensionally, this would be what we call a loss surface. And we start training by initializing the parameters in a random manner, and we can be anywhere on this surface. Training basically means navigating a surface in order to reach the global minima. And the stochastic gradient descent can sometimes get stuck in local minima points like this. So we need something to help us overcome this issue, something that can accelerate learning direction in order to escape these local minima points. Okay, so we have some other optimizer that I will show you. First off, I will just explain the principalities of how it works and what it's used for. I will not go into detail because a lot of maths is involved, but it's just something to keep in mind. When you use such an optimizer, which tasks is it suited for, and what are the benefits and cons for each one? So first of all, we have what's called AdaGrad, which takes the base learning rate that we set and then adapts it for each weight based on the update magnitude for that respective way. So it looks back on the history of updates, the update values, and then it adapts the learning rate for each weight. In which way? If we have large and frequent updates, then the learning rate decreases, and small and rare updates will mean a larger learning weight. This AdaGrad optimizer is suited for sparse data, For example, one good example for sparse data is if we were to do learning on data from a motion sensor. And usually the motion sensor captures data all of the time and only triggers when it detects motion. You can have a whole day without someone passing in front of the sensor, and then 5-second movement is detected. This is an example of sparse data, and AdaGrad can be can be can adapt well to this situation, but it's also a bit slow, just like stochastic gradient descent, and especially on plateaus or local minima. We also have root mean square propagation. It's an improvement for AdaGrad, and it places more emphasis on recent values. So it's not it doesn't take into account the whole history of updates for a weight. It places more emphasis on recent values, which are more relevant for training, and this prevents slowing down by old values. Ada delta is just a smarter optimizer, or smarter variant of root mean square propagation. And one important thing to remember about Ada delta is that it does not require to define an initial learning rate. It is adapted internally, automatically. This can mean slightly slower learning because it also has to learn the learning rate. But if you don't want to bother with that, you can use this optimizer. And probably the most versatile and the most used one for deep learning is Adam, which also combines what I told you before with momentum. Momentum is similar to what AdaGrad does by adapting the learning rate for each weight, but it adapts it by not the values of updates, but also their signs, their direction, because you can update the weights with plus or with minus. So this is what momentum does. It looks for the direction of the update and applies acceleration based on that. So if we have a lot of updates in downward or with minus, then we have a lot of acceleration in that direction, which speeds up the learning by a lot. And like I said, Adam is the most popular. So like I said, the general purpose working well on noisy data or sparse networks. And then we have at the bottom stochastic gradient descent, which is for simple tasks or didactic use cases. Okay, this is an animation that compares some optimizer. Adam is missed in this animation. We can see that root mean squared optimizer and AdaGrad are the fastest, followed by momentum, and NAG is also a type of momentum. Okay. And we can see that stochastic gradient descent is the slowest compared to the others. Okay, one more thing that I want to discuss about training is how do we initialize the parameters, especially the weights, because they are the most important type of parameter in a network. It can affect the speed of convergence or the speed of training stability, and also the ability to escape local minima. I remember that I had this a problem with initializing weights during one of my projects in university, one of the final projects. It was a more complex task of deep learning. And I remember that I wasn't paying attention to how the weights are initialized, and I didn't understand why the weights would become undefined at one point, and then the network would cease to learn because the weights are undefined. And I spent like a whole week. My poor laptop was was training for a whole week nonstop, a lot of tries, trying out different things, but I just didn't think about weight initialization and until I asked a colleague, and he said that he also had the same problem. And I solved the problem in like, I don't know, 5 minutes, and then I had progress in like half an hour of training. I was already seeing progress after a whole week of struggling. So it's very important to if you experience problems like vanishing gradient where the gradients become too slow and you have very slow learning, or exploding gradients which can cause undefined values for weights, you can look into how the weights are initialized. Most of the time when using modern frameworks for deep learning, it is okay to use the default weight initialization, but keep in mind that uh, when you have problems and you don't seem to find the cause, remember that you should also check how the weights are initialized. Weights are initialized using random small values between 0 and 1, following different distributions. Because we use random initialization, the training procedure usually follows a non-deterministic path. So of course, we use a random initialization, which means we don't have the same, we don't really have the same results when doing two different rounds of training. So we can overcome that by using random seeds. For example, if you had a look on the Python notebook that I sent you on Tuesday, which we'll also analyze today, you will notice that I used a random seed in order to have the same result, repeatable result over time. These are some of the weight initialization techniques. The first one is ideal when using the ReLU activation function. If you want to use other activation functions such as sigmoid or hyperbolic tangent, you can use Javier or Glorot initialization. Or you can use random initialization following a uniform or normal distribution. It is simpler to implement, uh, a bit faster, but that's not important because it's only done once, and this can lead to problems like vanishing or exploding gradients. If we were to use 0 or constant initialization, that would mean that all the weights would start from the same value. And when we do backpropagation, all the weights on one layer will be updated the same. Different layers will have different values, but on one layer, all the weights will have the same value, which doesn't bring any usefulness, because same value over one layer for every weight means that it is equivalent to one single weight, which is not ideal. So never use 0 or constant initialization. Okay. One more thing I want to show you before switching to demo. Some of the most popular and most used neural network types today. I told you about the feed-forward neural network, the simplest way. This is what we discussed until now. It is used for simple classification or regression tasks, and it's also good for educational purposes. We have recurrent neural networks designed for sequential data, where the order in which the data arrives is important. For example, when we talk about the weather or audio signal. They are also used in natural language processing, which is what LLMs come from, natural language processing. LSTMs, long short-term memory networks, they can capture long-term dependencies, also used for natural language processing, for sentiment analysis, and chatbots. And transformer networks are the most important ones today for large language models, because GPT, BERT, or Gemini, they are based on these types of networks. And these types of networks, we will talk about them in our presentations next year. Okay, some other use cases for network. We have generative adversarial networks used for image generation, example, deepfakes or DALL-E that generates images based on prompt. And also image upscaling. If you use NVIDIA GPUs for gaming, for example, they have a technology called DLSS, where you render the game or whatever you're working on a smaller resolution, and then they use this kind of networks to upscale it to a larger resolution, and you get better performance because the GPU doesn't work as hard to render everything at a large resolution. We also have convolutional neural networks that are specialized for grid-like data, like images, especially classification and recognition. We have autoencoders for unsupervised learning. Unsupervised learning is an interesting type of learning because you don't need labels for that type of learning. You have just the data, and then the results are evaluated by giving the network some rewards, some negative or positive rewards. For example, in university, I had to do unsupervised learning on a snake game, and the snake, if you remember the retro game Snake, you have to navigate some space in order to get some small rewards, and if you bite your own tail, the game is over. So I would give as input the neighboring tiles or the neighboring the close neighborhood of the head of the snake. I will give as input, and if I would detect an edge or the tail of the snake, then I would give a negative reward. If I would detect the small reward that you have to collect, I will give a positive reward. So this is how this type of networks learn. This is what unsupervised learning is. And we also have graph neural networks, which are some of the newest type of neural networks, very new technology. They are designed to process graph data, like social networks, 3D data, molecular prediction, and also they are used for recommendation systems. Very new technology, still in research. Okay, so this would be the PowerPoint presentation. I will switch over to a demo application this is the application that I wrote for my bachelor's degree. It is like a playground similar to what I sent you on Tuesday, a playground for training neural networks. We have visual representations because we use 2D data to train on. What I want to show you here is something that I did last evening, a use case in which we have overfitting. An example of overfitting. You can see the two data sets. A good fit model should just split this space in two, but because I used a very large model for this task and trained on 1,000 epochs, you can see here that it did some overfitting. It was very bad influenced by noise. Noise meaning that, for example, this blue point shouldn't be here, but this is the data that we have, and also this red point should not be here, and the model was thrown off by these types of points. This is a classic example of overfitting. Okay, let me show you some other cases. Maybe the difference between a sigmoid and a rectified linear unit. So I have a different type of data set here, this shape, which is not really easy to classify. Let's change to ReLU on all of the hidden layers. We also use sigmoid for the output layer because I want the outputs to be between 0 and 1. 1 being the blue outputs and 0 being the red ones. Okay, so let's use Relo for all of the hidden layers, and we use a learning rate of, I think for Relo 0.1 should be enough. So let's do it like this, and 500 epochs of training. Let's see where this leads us. So we can see that with a learning rate of 0.1, using Relo and 500 epochs, we get a very good result. We don't really have overfitting. It is a clear distinction between the two classes. And we can see here if we analyze the loss on the training dataset and the loss on the validation dataset, which is not used for training but is used for testing, which is new data for the model to classify, we can see that they follow the same path, and that means that we don't really have overfitting. You can see that it takes about, I don't know, like for the validation data set, like 300 epochs to reach the minimum value for the loss. Okay, now let's do the same stuff for using a logistic function. I told you that the ReLU is faster than logistic function. I think we can see that in action here. The same learning rate, but using logistic function on all of the layers, also 500 epochs. Let's see where this leads us. Okay, we can see that it was not able to do much in the 500 epochs. The loss is decreasing, but still way above 0.1 on the training dataset. Let's do 500 more epochs. So we'll have a total of 1,000. And you can also notice that it also takes a while longer compared to ReLU. Still nothing much. 500 more. Let's see if 1,500 are enough for sigmoid. Okay, nothing much happens. Let's use a larger learning rate and repeat the whole process. Maybe 500 will be enough this time with a 0.5 learning rate. Okay, still nothing much. Okay, so usually when stuff like this happens, when the network doesn't seem to learn much and we have a very high fluctuation in loss on both the training and the validation or testing dataset, this would be a sign of either vanishing or exploding gradients. If we were to do training by code, we then could examine how these values evolved over time. But I was hoping something like this would happen for you to see that sigmoid is not really the best activation functions, not even for simple tasks like this. Let's try one more time to see if we reach everything. And because in the backend code, I didn't implement anything to penalize the weights to reduce exploding gradients. And also, I didn't do anything in order to prevent overfitting, just so I can show you how it looks like. We have situations like this. Uh, and also, I also removed everything regarding weight initialization because we can see here that we don't have repeatable results. Let's try with hyperbolic tangent then. to see where this gets us. Should be quite similar to sigmoid because it's not really a big difference between them. Okay, doesn't seem to want to learn. Maybe the learning rate is too much. Okay, still nothing. So you can see that you have to do some trial and error and keep in mind problems like exploding or vanishing gradient. If you use modern training frameworks, this shouldn't really be a problem. This one that I use here is a bit more basic because this is an older app, like 3 or 4 years old. Yeah. So this is how we visualize training, basically. This is good for didactic purposes, but let's switch over to the real stuff. To the notebook that I showed you on Tuesday. So usually deep learning is done in Python because Python is very good for data science, data processing, everything. It has a lot of support, a lot of framework, a lot of libraries, which are very well suited for this type of cases. And these libraries are very well optimized, even though you might know that Python is not really the fastest language compared to other, but because of a lot of optimization was done and support was added for GPUs. For example, here in this notebook, we use CUDA, which are the cores for NVIDIA GPUs. We can also switch over to MPS, which is support for Apple Silicon. So if you want to run this notebook locally on your Mac, and you have M1, M2, M3, or M4 chips, then you can uncomment this and comment the CUDA code, and then it will run locally very fine. But because the runtimes from Google Colab use NVIDIA-based GPUs, and I remind you, when you start the notebook and you connect to the runtime, I remind you to change the runtime type to T4 GPUs, so we have faster learning using GPUs from Google. It's good enough for most of the cases. I mean, 99% of people do deep learning on uh, on Python. If we were to use someone else's runtime, then like here, whatever. But when we will use APIs for GPT or Google Gemini in the future presentation, of course, you can use other languages if they are supported by the APIs. I think we will continue with Python code. Maybe we will show some other examples in other languages like Java, but we'll see. So for now, let's focus on this notebook. How do these notebooks work? If you didn't have time to play around on Tuesday or until now, you can run blocks of code separately. You can also write text here. This thing is editable. I wrote everything here, the text and the code, in order to be as clear as possible. So when you connect to a runtime and then you run this block of code, everything remains in memory. So when I do imports here, I run this once and then use what I import here for in future blocks of code. So I don't need to do it again. Also, if you have you can have like a function defined here in this block. You run it, it is defined, it remains there. You can call it whenever you want in future blocks. Okay. If you want, you can also run the blocks, all of them at once. I mean, not at once, but sequentially, automatically. And you can see that everything was completed very fast all the way to the end. Oh, it's not done yet. I think it is still in the training phase, but we will get to that. So you can also run everything automatically. Okay, good. Let's start. So here we import some stuff that we will use, some basic standard libraries. NumPy is a very used library in Python when dealing with everything related to data science. It is a good library to handle data, basically, and also good library to handle the computations. For example, if you do matrix operations or things like that, NumPy has a lot of support for that. PyTorch is what we will use today. It is one of the most used frameworks, both for educational reasons and also in practice for deep learning. It has support for a lot of types of networks, support for importing data. For example, if you want to do like an educational project, then you can access already cured data that you can learn on. A lot of already created network architecture. It is a huge library for deep learning, probably the most used today. Some alternatives include TensorFlow. This is from Google. I haven't used TensorFlow in a few years, but the app that I showed you beforehand uses TensorFlow because this is what was popular 4 years ago when I did my bachelor's degree. 3 years ago, I don't even remember. Okay, so PyTorch is usually the safe bet when you choose your deep learning framework. And a lot of papers are also include PyTorch code. So if you read a paper regarding some deep learning, they usually use PyTorch. It is basically the standard. Okay, so PyTorch offers support for CUDA GPUs and MPS. I'm not sure about AMD GPUs. I don't think so. I haven't tested, but you can check it out if you want. But for this specific reason, we use Google Colab. We don't have to worry about that. We just want to match what they offer, which is NVIDIA GPUs. So here we import Torch from PyTorch and we check the version. Here we check if CUDA is available, and if it is, then we set this device parameter to use CUDA. If not, we can always use the CPU, but it is very slow compared to GPUs, even on small tasks like this. Here I have a section which I will not really go into detail. It talks about what PyTorch calls tensors. These tensors are representation of data in one dimension, two dimension, or whatever dimension you want, three-dimensional, four-dimensional, whatever you're working with. Tensors are a way to represent data, some kind of special lists, I will call it, but they are just some kind of special data representation for PyTorch, which have a lot of optimization for any type of operation. You can do a lot of operations with tensors. You can initialize them randomly, or using a nested list, or using predefined values, or using different probability distributions. You can do a lot of stuff with tensors. One thing to keep in mind is when you do learning, how do these tensors are used? They are used in order to represent the weights. They are saved as tensors, and also the input values that use for training from the input dataset, they are also used as tensors. And the learning is basically done by using matrix multiplication. Matrix, okay, we can also have three-dimensional or four-dimensional or whatever, but at core, we have matrix multiplication. So this is how the data is represented. So when you're working with tensors, it's important to keep their shape in mind. So for example, we have here a three-dimensional tensor with I don't know how to call it, 2 lines, 3 columns, and then 4 values for each element. So yeah, I will show how a tensor looks inside the network. Yeah, and you can do operations like addition, multiplication, swapping, translation. You can switch dimensions. You can remove dimensions. They are very versatile. Here I have an experiment to show you the difference between CPU and GPU time. I create a tensor with 5,000 lines and 5,000 columns, and then perform some multiplication, which is not really easy to compute. And I compare CUDA, which is NVIDIA support, with CPU, and you can see here that CPU took like 4 seconds and GPU a fraction of that. So this is why it is important to use GPUs when learning. Here I set a manual seed in order to get the same result. If you want to have a more natural and more deterministic path to learning, you can remove this seed. And here is what we'll be working on today. It is similar to the XOR function, but moved into continuous space because we have like clusters of points instead of 0, 0, 1, 0, and like that. So we have clusters of points arranged in a fashion similar to XOR function. Why did I choose this dataset? If you remember from the first presentation, this dataset is not linearly separable, which means that it cannot be classified by a single neuron or by a perceptron. So we need a larger data set for that, but it's two-dimensional data. I will show you how the data is represented. Okay, how do we define a model? In Torch, we use Torch functional, and for the model architecture, we used modules. A module can represent a layer. You can represent it as multiple layers and then use it as a layer in other modules. So you have modularity, like the name suggests. You can have very big architectures using these modules. Like you can use whole networks as layers for a bigger network. And for example, transformer networks, this is what their architecture is like. It's very big, and they use whole another type of networks as simple layers. So this is what our classifier for this task will look like. The input layer has 2 inputs because we have 2 coordinates of 2-dimensional data. We have 4 hidden neurons on the hidden layer that will use the sigmoid function. No, this is the hyperbolic tangent function. For this task, it is enough. And the output will be a single neuron because we either have values close to 0 for one class or values close to 1 for the other class. Okay, so here is where we define our network as a Python class. It should implement 2 methods. This is the constructor where we have the dimensions of the layers as parameters. And we also have to define the forward function, which means how do we pass the data between these modules, or in our case, between these layers. Okay, so we have 2 layers. We call linear 1 because linear is the type of layer that we use and we discussed so far, which has the dimension of number of inputs and number of hidden. It's this layer right here. Okay, and then excuse me, it's basically this layer like right here, because it has as input the number of inputs and as output the number of hidden network, the hidden neurons, because the input of the output of the layer. We then apply a hyperbolic tangent function, and then we have a last layer which has the number of outputs as output, which is 1 in our case, and the number of hidden neurons as inputs. We define it this way because this architecture of network, it's called feed-forward or fully connected network, is all of the neurons from one layer are connected to all of the neurons from the next layer. And it is called feed-forward because the output for one layer is the input for the next. And we have like a chain of layers. So this is how we define the forward. We basically show the order in which the data passes in the network here. And the Python code, Python in general, is, I think, quite easy to read. You don't have to worry if you don't have experience in Python. I think it's easy to understand what Python code does. Especially here, in most of the cases, I refrained from using any specialized syntax. And the syntax is anyways easy to learn. Okay, so we define our network with 2 inputs, like we see here, 4 hidden neurons and 1 output. This is our model. If we print the model, we get what we defined here in the class. We can also see here the shape of each, the shape of all of the parameters. So on the first linear layer, we have 4 lines and 2 columns because we have 4 neurons on the hidden layer and 2 on the input layer. So we have how many? 4 times 2 weights. Each weight is on this edge. Each edge represents to 1 weight. So we have 4 times 2 weights, 4 lines, and 2 columns. For biases, 1 bias for each hidden neuron. We have 4 biases here. And then for the next, for the output layer, we have 1 line and 4 columns for weights and 1 single bias for the output. What I want to, okay, I will get to this a bit later. Let's talk about the data. So here is the data for PyTorch should use this torchutils data package. You define a class that implements this data structure, and you have to specify, of course, the constructor, the init function. You have also to implement the getItem method, which returns an item from the input data set. Given an index, we also have to implement the len method, which returns the size of the input data set. Okay, so I will not really go into details how I create the input dataset, because most of the time when you do learning, you can get a dataset from the internet. You just do a curl and get the dataset and then load it in the data loader and just do learning on it. Here I create a custom dataset. But if you're curious, this is why I have here, I split the whole size of the data set in 4 because I want to have 4 clusters. I want the centers of the clusters to use these coordinates similar to the XOR function, what I would give to the XOR function as input. And then I use the make blobs method from sklearn. Sklearn is another great framework to use also for data science, generating data sets, editing data sets, and things like that. This method, I specified the number of samples in total, the centers, This is the standard deviation of each cluster. It is how much of this cluster is spread. If you have a lower standard deviation, then it's more compacted. If you have a larger one, it will be more spread. Let me show you if you're curious. For example, here, this is what I call noise here. If I increase the noise to 3, you can see they are more spread, which is more useful, noticeable on smaller sizes. So it will be a bit more spreading between those. This is related to standard deviation, and we also use random state, the same seed, in order to get the whole generation the whole time. For labels, we use XOR in order to get the labels, and then apply it in continuous space. And that would be it. The size of the dataset we just call self.size, and the get item for a given index we return. In Python, you can return 2 things at once, and it will return as a tuple. We need to get the points, which is the data that we learn on, and the labels, which is either 0 or 1, depending on each class. So here, if I create a data set of 200, then I can call the len method and data set of something. We get an array of 2 dimensions of type float, and this is their class. Is 0, probably the orange class, if I remember correctly. Oh, yes, the orange class. Here I wrote some code to visualize the generated data set. I will not really go into details with that. I use PyPlot. This framework is usually used for plotting things. Okay. The data loader class is what handles the data after we define it. So we talked about mini batch training, splitting the whole data into smaller chunks. This is what a data loader does. Before starting training, it splits the data into smaller chunks. We define the chunk size or the batch size here. It is a parameter of the data loader class. And the data loader is also tasked with feeding the data into the neural network. One other parameter important here to remember is shuffle. What shuffle does is mixing the data before splitting it into chunks, so we don't have the same sequence. And this introduces a bit of diversity in the data and helps the model learn faster. Shuffle on true is usually set when doing learning or training, but when we will do evaluation on the validation data set, there is no need to use shuffle. It just slows things down. Other than that, number of workers is how many processes should use in the background to load the data. Don't need to worry about that at the moment. Pin memory is if you want to use the GPU memory to keep the data, maybe speed up the training a bit. I don't think I bother with that for now. And drop last, if you use a batch size that does not perfectly divide the whole data into equal batch sizes. For example, if I have 20 elements as input and I use a batch size of 7, then the last batch will be smaller because it's not divided perfectly. And if you set this to true, then it will ignore the last batch. No need to do that now, because for the data set of 200 points here, I use a batch size of 8 and shuffle on true. If you want to visualize how a batch looks like, it has the size 8 lines and 2 columns. Why 8? Because this is the size of the batch. So we have 8 elements from the input dataset. Each element is of size 2 because it has 2 dimensions. So this is the input data that we will go into network when training. And the labels are of size 8 because we have 8 elements, 1 element for each element, one label for each element in the batch. So this is the size. Okay, these are the steps of learning. Like I said, I will remind you, get a batch from the data loader, obtain the predictions, so doing feed forward. We calculate the loss or the error. We backpropagate the loss using gradients, and then we update the parameters to do learning. We will use cross entropy for this task. This is the binary cross entropy variant. I told you that cross entropy is usually used when we have more than two classes, so binary classification. But in this case, there is an adapted version of cross entropy that works with this. One important thing to notice is that, like I showed you here, I use sigmoid for the output layer because I want to map the output in the range 0 and 1, because class 1 is one class, class 0 is the other. Here, if you paid attention, I didn't specify where I created the classifier. I didn't specify anything about the sigmoid, and I did this by I wanted to do this intentionally because you have to remember when using loss functions here in PyTorch, usually there are two variants. You have a simple one and one with logits. And you use the logits one when you don't apply any activation in the output layer. So it will not expect output between 0 and 1 or whatever range that you expect. This logits version of the loss function does not expect any bounded range, but it will apply sigmoid automatically in this case. And I use this approach to apply sigmoid together with the loss function with this logits variant because it is a bit faster and more optimized. So this is what I use here for loss. Okay, and as optimizer, SGD stochastic gradient descent is enough. For this case, I use a learning rate of 0.1. It's enough for this case. Okay. For training, we redefine the data set with a size of 2,500, and we use the data loader with a batch size of 250. So we will have 10 batches and shuffle on through. They will get mixed from one epoch to another. We don't have the same batches, so more diversity in the input. So first of all, we prepare our model by pushing it to our device. If you remember, we set the device to CUDA, so to use the NVIDIA GPUs for this runtime. So we push it to the device, and then we define the train function. We will have as default 100 epochs. Here I change it to 300. These default values in Python, you can set them here when you define them, the function signature, and then you don't have to specify the parameter again because it is set by default. So this is why you have a value here. So we have the model, we have the optimizer, we have the data loader, we have the loss function, and the number of epochs. First, we set the model in the train mode. This will apply some internal optimization for speeding up training. This list here is used to compute like a history of loss in order to plot it, just like I showed you here. Here at the bottom, over the span of a number of epochs, we want to see how the loss or the error evolves. Also here, this is what we use them for each epoch to save the loss. This is a for loop. This method is not important. It's just for showing this loading bar here. It's just for aesthetic reasons. Okay, so we start an epoch, then we start to take elements from the data loader, from the data set. Okay, we take one chunk, we push it to the device, we take the labels from the chunk, we also push them to the device. This is what the feed forward looks like. It's called, we just call the model with the input. And this is how we do the prediction of the network. One thing to keep in mind is that the output of the network, because it received a batch which contains multiple elements from the dataset, the output will also be of batch size. So it will do prediction for 25, what was the batch size here? For 250 elements at once, it will do prediction. It will return as a two-dimensional list, which will have one last dimension, but we don't need that one last dimension, so we do squeeze. So we reduce the dimension from batch size 1 to batch size. Instead of having the output as 250 lines and one column, you just have the output as a list. This stuff about sizes, you just have to keep attention to them from situation to situation. So, but if you get an error, it will specifically say that it was expecting what size, and you give another size. So you can do transformation on the spot. Okay, we compute the loss using the predictions and the labels. Here, before doing any update for one batch, we set the gradients to 0 in order to be prepared for a new round of updates. If we don't do that, then the gradients will accumulate, and usually this is not the case that we expect. So we have to do this manually. Loss backward is what does the backpropagation of the error in the network. It computes the gradients, it does all the computation for us, so no need to do much. And step is basically applying these updates to our parameters. Okay, and we do this for each batch from the data set for a number of epochs. We train here for 300 epochs. This is how the loss decreased over time. I think here I have the loss plotted here. So it took like what? 200 epochs to reach close to minimum value. Okay. After we do training, what do we do with the model? If you want to reuse it, you can save it on the disk using the state dict. Dict comes from dictionary. Dictionaries in Python are equivalent to the maps in Java, for example. So we use this state dict function, which returns a dictionary of everything in the model. Here, for example, is the biases for the first layer. These are the weights. You can see how they evolved. Strange values, but this is what gives us the learning. And then this dictionary, you can save it using Torch save with whatever extension you want. It's serialized and deserialized the same. After saving it on the disk, you can then load it using Torch load, and then you give the path. You have to create a new instance of the class, and you have to use the same class because we save the model with this architecture. If you use a class with different parameters or a different class, it will obviously give an error because it doesn't match with what we saved on the disk. And you can see here, this is the original model that we trained, and this is what we loaded from the disk. They are identical. The only difference is that this model is already loaded on the GPU. And after we do training, the last step is to do evaluation. How do we evaluate? We have to compute the accuracy, And the accuracy is computed by dividing the correct number of correct prediction to the number of all of the predictions. So we create a different data set which was not used for training, new data set which the model didn't see for training. I just used here a batch size that does not divide this size, just so I can show you that I used the drop last parameter. So I say that please don't ignore the last batch, even though it is smaller, don't ignore it. And here I set shuffle to false because we don't need to shuffle when doing evaluation. We don't do any learning here, we just do predictions. So no need to shuffle. To speed up the things a bit, the eval function is similar to the training one. The loop looks, it's quite similar. Just remember to set the model to eval mode. It just optimizes it for faster evaluation, no learning whatsoever. So we deactivate the gradients here because we don't need to compute gradients because we don't do learning, we just do prediction. And then for each batch from the input that data set, we push them to device, we do prediction. Okay, we do one more squeeze because I showed you the output of the network, the size, and what it is easier to use. We apply sigmoid because we didn't specify it in our network architecture. And then here with the output of sigmoid, which are values between 0 and 1, we do binarization. So values below 0.5, we consider that those are predictions for the 0 class, and values above 0.5, we put them in the 1 class. So basically binarization. And then here we compute the accuracy, and we see that we get 100% accuracy. This happened because we have a small data set, a simple data set, and a small network. In reality, you will never reach 100% accuracy when doing like real training on real stuff. But you can hope for the best. So don't expect 100% accuracy when we deal with more complex stuff. And this is just one last method. I will not go into detail of showing the visualization of the output of the network. What I basically do here is take each and every point here in the background between these ranges, 0.5, minus 0.5 and 1.5. I take each point, not all of them, of course, and do prediction. And then using the predicted value, I choose a different color if it is more towards 1 being the orange class or more towards 0 being the blue class. And this is basically an example, a simple example of training. If you're curious how much this training takes, let's run the train loop again. Okay, I didn't need to run that. The function was already defined. So let's see how much 300 epochs takes like. So in our case, a few seconds. Using this free runtime from Google is not really the fastest. If you want, you can purchase some additional compute units for faster GPUs. Yeah, or if you run locally and you have a good GPU, it will be even faster. Of course, like I told you about when I talked about weight initialization, I told you that it took a few days for me to train that example of reinforcement learning when unsupervised learning when I didn't kept in mind the weight initialization. So usually learning takes a lot. This is a small example, but given the data size and the size of the network and what computational power you have available, the training can take a lot. So yeah, this would be basically it. If you played around with the notebook, you just run it. It should run, no problem. If you play around, change some things, remember to save in your drive in order to save the progress. And if you have any questions, that would be the time. I would gladly answer them. I know it's a lot of info or new info, but it's good that it's in Python because Python is, I think it's easy to learn and easy to read. If you know one other language, then Python is easy. It's easy to understand. So thank you very much for your attention. If you have any questions, please, I would gladly answer them. If you want, you can send me a message on Teams. We can speak whenever. If you want to look around on this notebook or maybe try something else, I'm always available uh, to help.
Also, it's worth mentioning that we also could use pre-trained networks, just not to start from scratch with these models for neural networks. Also, I can give you a nice website where you can find pre-trained models and also datasets if you want to use and play around. Yeah.
Yeah, Hugging Face, it's a good site and community where you find data sets, models, whatever you want, and use pre-trained models. You can take models which are already trained and then do a bit more training on them. This is called fine-tuning. When you adapt an already trained network for a specific use case or enhance the network with something else. Okay. So, any questions?
Hi, I have one question. I
Yes,
just
please.
didn't understand how we define the value for the learning rate because you use different ones and we had different results.
Yeah.
So that part I didn't catch.
Yeah, so learning rate is usually set empirically. So you have to experiment a bit to get the best learning rate. But when you use specific activation functions, like I showed you here, if I go back. So I used hyperbolic tangent, which I know for a fact that it is slower compared to ReLU. Then I have to compensate a bit with a larger learning rate. But maybe 0.5 is too large because we had a lot of fluctuation in the validation. So I would try a smaller size and do training again. You don't have to do the whole training. You just have to start a few epochs and see how the loss decreases. And if you have no decrease over a large number of epochs, or if you have large fluctuations, then you know that you have to update some things. But usually learning rate is set empirically. Or if you use the ADA delta optimizer, I told you that that optimizer does not require an initial learning rate value. It learns it by itself. But that means a bit of slower learning compared to other optimizers which have adaptive learning rate, but start from an initial learning rate value that you give yourself. So the best way to get to the best learning rate is uh, to experiment, basically. But usually, values between 0 and 0.5 are always a safe bet. 0.1, 0.05, 0.25, values like this, round values. You can start from them and then do a bit of fine-tuning to get better results. after experimenting. I hope this answered your question.
Yes, thank you.
Okay, thank you for your question. Any other questions?
Yes.
Yes, please.
Can you hear me?
Yes.
Yes. Okay. Obviously, there is a lot of parameters here when we define this neural network. And is it possible to train a network without any help of some person? So completely automatic.
I mean, you have to define some things for yourself. If you start from scratch, if you download the model from this site that Christy sent, for example, Hugging Face, then the model usually it's already defined with all of the parameters, like all of the hyperparameters, like what activation function it uses, or what are the size of the layers, or the number of layers, or the optimizer that it used. But if you start from scratch, you have to define these things for yourself. You have to set the shape of the network, what activation function you used, what optimizer you used. But you have to keep in mind before starting, what is your task? Are you dealing with sequential data? Then you use an adequate network designed for that, like recurrent neural networks. You then, for the shape, I don't know, you can experiment, you can search a bit what is recommended. For the optimizer as well, use something adequate for sequential data and things like that. So you have to do a bit of research before starting training on something, and you have to define some things for yourself. But if you just want to play around to see how it looks, I send the link on Tuesday as well. There is this site called TensorFlow Playground for starting up, just to see how things work visually. You have here a model with one hidden layer and 4 neurons starting, and this is the data set. And if you start training, you can see how the model learns. And here you can see what exactly does the neuron divide in this sample. For example, this neuron divides this line, and then this neuron divides this line, and all of them together compute this shape here. And you have, if you hover here, you can see the weight value. Bolder line means a larger value. Yeah, so if you just want to play around to see how it looks and then start with code, you can start with this TensorFlow Playground. I will send the link again here. But yeah, to answer your question, if you start from scratch, you need to define those things yourself. The parameters, the hyperparameters, the parameters are initialized. I hope this answered your question.
Yeah, thanks.
Thank you for your question. Okay. Any other questions? You can also write them in the chat if you want. It's easier for you.
So I guess that's it for questions for today. Feel free to use the chat or to contact directly Christian and Vlad with questions. Thank you everyone for joining. Thank you Vlad and Christian for preparing the material. And as we are preparing some additional sessions for next year, my colleagues will leave a feedback form on the chat so they can improve these future sessions. So please take a few minutes of your time and fill the feedback form. Thanks everyone.
Yeah, there are a lot of questions, but all of them are options with select options, so it shouldn't take long. It would help us very much if you leave feedback. Okay. Yeah, so you have the link for the notebook on the chat from Tuesday. I will also send the link for this presentation, for the PowerPoint presentation, if you want to have a look. And whenever you need any help, please hit us up on Teams and we would gladly help. Okay, then. If there are no more questions, thank you very much for your attention and happy holidays, and see you next year on future presentations. Have a
Happy
good day.
holidays. Thank you for your
Thank
attention.
you. Bye.
Thank you.
Bye bye.
Thank you.
Bye bye.